Okay, so the next two kind of concepts are really the same idea. They're tied together intrinsically. They're going to be something called the chain rule and something called implicit differentiation. Implicit differentiation, all it really is the chain rule. And so we're really just kind of spreading one kind of concept and blowing it out as much as we can. So we're looking in sections 3.4 and 3.5. That's the idea, at least. And their headlines, as you might read in, the table of contents, are the chain rule and implicit differentiation and logarithms. This will be kind of a tent pole for future differentiation. There's going to be an entire world of derivatives that open themselves up to us because of the chain rule. And it's something that will be extremely important kind of moving on throughout all of your calculus career. And where it's sitting is this. Okay? Here's the name, the chain rule. But here's the idea. How do we find derivatives of compositions of functions? That is, if I know f prime of x and g prime of x, can I find the derivative of f of g of x? So if I know how to take the derivative of f, and I know how to take the derivative of g, what happens if I shove g inside of f like some kind of mad turducken, and then take the derivative? So what are examples of some composition functions? Let's say g of x is x squared plus 1, and f of x is the square root of x. Okay. So here are two different functions, each of which is very easy to differentiate. But if I push them together, if I replace all of the x's in f with g, I get this composite expression, which is difficult for me to differentiate where we are right now. Right? Notice that this is different than just multiplication or division. There's not an operation that's being a traditional type of operation that we would see on a calculator taking place between these two expressions, right? Another example might be what? G of x equals, how about x plus 2, and f of x equals e to the x. Then f of g of x is e to the quantity x plus 2. That's very tiny. I'm sorry about that. That's better. E to the x plus 2. E to the quantity x plus 2. I know how to take care of e to the x, but if you start doing other stuff up there, I don't know. Right? So e to the bunch of stuff is going to be very difficult for me. Right? Bunch of stuff raised to a power is going to be very difficult for me. Right? And these are kind of two flavors that we might see. Right? If I have f of x raised to the nth power, how do I take that derivative? If I have e raised to some whole function, how do I take care of that expression? These are the main two types of thing that we might see. Just dealing with the types of function that we know how to deal with right now, right? We know how to take care of x to the nth power, and we know how to take care of e to the x. But if I have bunch of things to the nth power, or I have e to the bunch of things, I'm going to have a hard time differentiating these. So that's where this chain rule, quote unquote, right, is going to come in. Right? The chain rule is going to give us a process that we can use in order to evaluate these types of derivatives. Little do we know, little do you know, you already know how to do this. What, you say? I think that I would know something that I knew. So here's a question. Let's say, for instance, you know something like, we've got this function f of x, and it measures something like this. It measures miles traveled, right, on X gallons of gas. Right? You have used X gallons of gas, and this tells you how many miles you have traveled on that tank, right? On that many gallons. Cool. So what does f prime of x measure? It's certainly measured in miles per gallon, right? F of x is in miles, so the outcomes are in miles, and the change in x's are measured in gallons. So, right, this is rate of change, instantaneous rate of change in miles at x gallons, right? Used, right? It's in miles per gallon. Right? This is how fast you're going in terms of gallons, right? How much gas are you using in order to go how far you're going? Let's say x is a function of m, right? Gallons of gas that you have is a function about how much money you have pumped into your tank, right? So you tell me how much money you've spent, and I can tell you how many gallons that you have. Right? So what's dx dm? Yeah, so I'm measuring how fast the gallons are changing per, m is in miles, it's, what's m? Money, right? Right? This might be measured in gallons per dollar, right? This is the rate at which the number of gallons going into my tank is changing based on how much money I'm spending. these are two things that you probably do if you drive places, right? And you care about how much money you're spending doing it, right? How many miles to a gallon am I getting on my car, right? Well, when I fill up, I go in and I look at my odometer, and it says you've gone this many miles since your last fill up. And then I'll look at the tank and I say, oh, well, that's how many gallons I just put in. And then I divide the two to get an average rate, right? To know how many gallons per mile or how many miles per gallon my car gets. And then I also know this other rate of change, right? I also know how much it's costing me to put a gallon of gas into my car, right? So if I wanted to know how far a dollar is going to get me, now I'm wondering about how are miles changing as dollars change, right? Yeah.
Clarification question is, does that mean M is a function?
M is a value. It's a value of money.
So it's
Right?
just a single value.
It'll be a single value.
It would be something that the problem would sometimes give us that we would plug in at the end.
Yeah, so kind of in a picture here, I might have, here's my money, and you tell me how much money you want to spend, and I can tell you how many gallons of gas you can get. Oh, there we are. Right? You tell me money, I tell you you can get this many gallons. Right? You tell me how many gallons you want to burn, and I can tell you how far you can go. And so these kind of intermediate rates are easy for me to find, right? And I find them on average a lot of the times when I'm at the tank, right? Dollars per gallon or gallons per dollar is right there given to me, and then miles per gallon I figure out on average when I look at it. Right? But what I might really be interested in, right, is not that, this. What's the rate of change in f of x with respect to m, right? As the amount of money I'm putting into my car changes, right? How is the distance I'm traveling changing? Right? That would be an interesting rate for me to know, right? How many miles per dollar does my car get? Right? That's much more useful to me on average than the others, because that's something that my budget cares about. If I'm going to have to commute 40 miles to work, is it going to be worth it to me to pay the money to actually get a paycheck, right? My friends wanted me to go up to, Put-in-Bay for a weekend, and we're going to drive. And there's going to be, there's going to be an expense in driving up there on top of, all of the money I spend running around on an island for a couple days. Whew. So, so the derivative with respect to money of f of x, what's this measured in? F of x is miles traveled, and m is money spent on gasoline. So the derivative with respect to m of f of x, what's that telling me? And what's it measured in? Yeah, it's going to be measured in miles per dollar. It's telling me how are the miles you're traveling changing as the amount of money you put into your tank changes at an instant, right? How might I figure this out? How would you figure it out? You know how many miles per gallon you're getting, and you know how many gallons per dollar you're getting. ideas? Let's do this. Right? Your car averages, so we're talking about average change here instead of instantaneous, but that's fine. Your car averages, let's say 24 miles per gallon. That seems like a reasonable number to assume for some of us. A gallon of gas, right? Let's say is about $3, right? So we get 1/3 of a gallon per dollar. How many miles per dollar do you travel? One gallon will give me 24 miles. It's 1/3 of a gallon per dollar. I put $1 into my tank. How many miles do I get to drive? Just got to get home. Scrounging change out of seats. 8 miles. How'd you get that?
I did it because you get 24 miles a gallon.
Uh-huh.
So 1/3 of a gallon is going to get you 8 miles.
Right, because 1/3 of 24, right?
Right.
So we're multiplying, right?
Yeah. 24 times
24 miles per gallon times 1/3 gallon per dollar is 8 miles per dollar. Okay. Notice that gallons cancels out with gallons, and so we wind up with miles per dollar in the units. It's always a good kind of sign that, uh-oh. Ooh, we're back. Right. Units are working out pretty nicely. So 8. So multiplication is happening. Okay. And this is the rate of change. This is how distance is changing with respect to gallons I've put in. And this is how gallons are changing with respect to the money that I put in. This is the derivative of f with respect to x, and this is the derivative of x with respect to m. And check this out. Look, dx, dx, these look like they cancel out. And we get df, dm. This is one of the great things about Leibniz notation, that even though this isn't a fraction, right? This is a single expression, df dx, right? We think of this as an operation that's happening on f, right? F is being taken from a value to a rate at which that value is changing by this operation. There's the picture. This operation says you plug in f and it's a value, right? And it comes out as a rate that value is changing. So this isn't really a fraction, but it's kind of what happens as a fraction kind of like limits down to like a 0 over 0 type of situation, right? And this works out so nicely, right? That it just looks like the dx's will cancel if I think of these as fractions. And I get this df dm. So despite the fact that these aren't fractions, the Leibniz notation says if you treat them like fractions, this kind of true fact still works with your notation. It's one of the wonderful things about Leibniz notation. In that kind of f prime notation, this reads like what? The derivative of f of g of x is f prime of g of x times g prime of x. This, right, understanding where this is coming from is a little bit more abstract, I think, in notation than this. So for those of you that have hated the Leibniz notation, here's a reason why you might be fond of it. So this holds true in general. These facts are the chain rule. This is how we're going to differentiate composite functions. In general, we're going to identify an inside function that's kind of happening, and then there's this outside function that's taking the inside function to somewhere else. Okay? Because what's happened is we've taken a function g of x and we've plugged it into a larger function f of x. So you may hear me or other folks or Stuart, or the author of our textbook, refer to inside and outside functions. So in these previous examples that we've seen, we might see an inside function, x squared plus 1, and then an outside function, this square root. Or here, there's an inside function, this x plus 2, and then an outside function, e to the x. Okay? There's this little function happening inside of a larger function. There's this little function happening inside of a larger function. So let's look at these two examples in particular and see if we can find out what their derivatives are now that we know the chain rule. I'm going to write it this way. I like this notation a little bit better for the prime notation. I think it's a little bit cleaner. I'm thinking of u as a function of x. So you give me a value of x, and I will give you a value of u. And this is f of u in here. Right? So here I have a function of u, but what's really happening is I'm taking the derivative with respect to x. Notice u is not x. So what happens is I take f prime like I normally would, but I leave that inside function exactly the same. I'm just going to say, oh, the derivative of f is normally f prime, so f prime. And this u, it's not an x, but we'll just kind of leave it alone. And then I multiply by the derivative of u at the end to kind of adjust for the fact that u has not had its derivative taken. The idea here is that the derivative of f with respect to u times the derivative of u with respect to x is the derivative of f with respect to x. Here's the Leibniz notation again, where it looks like the u's cancel. So here's a function, the quantity x squared plus 1 raised to the 1/2 power. Okay? It's a composite function, right? Notice the outside function is something to the 1/2, and the inside function is x squared plus 1. Okay? So I could think of it as kind of making this substitution, kind of breaking it back into two parts. Right? Here it's one thing where these two functions have kind of been mushed together, but I can break it up into its composite parts. There's an x squared plus 1 part, and there is a something to the 1/2 part. Right? So u is x squared plus 1, and this entire expression is u to the 1/2. So what the chain rule says is that f prime of x, I'm differentiating u to the 1/2. So what's the derivative of u to the 1/2? Yeah. 1/2 u to the negative 1/2, just like normal. Right? But you will notice that I want the derivative with respect to x, not u. Right? X is changing, not u. And so what I'm going to do is I'm going to multiply now by the derivative of u. So you get a derivative, you get to take the derivative just like you normally would, but then you've got to multiply by u prime because I'm taking the derivative with respect to x. What's u prime here? What was u? U is x squared plus 1. So u prime is 2x. Easy to take the derivative. And I'm wanting things to be in x's, right? So there's no reason to leave things in u's. So this is 1/2 u. U is x squared plus 1 to the negative 1/2 times u prime, and u prime is 2x. The 2's will cancel. I don't like this negative exponent. So a little bit of algebra will give me x over the square root of x squared plus 1. This is a positive exponent, so it's fine in the numerator. This is a negative exponent, so the whole shebang here moves to the denominator. Questions about this? Yes?
Can you explain why you plugged in just x squared plus 1 instead of all that to the 1/2 power? That's where I got lost.
All right, so here this is x squared plus 1
Right.
instead of the square root of x squared plus 1.
Right. Yeah, I just want to know why you plugged that in instead of.
Because this is u, right? It's u to the negative 1/2. And I defined u to be x squared plus 1, right? It's not all of f, it's just x squared plus 1. So I've just replaced u with itself. So let's see another one kind of like that. Okay? What about g of x equals e to the x plus 2? I don't like that. It's complicated. So I'm going to just try to mash that x plus 2 into a single variable. Right? This is a composite function. I'm going to say, I don't like e to the x plus 2. It's complicated. Right? There's a duck inside of this turkey and a chicken inside of that duck, and I'm not happy. Right? I'm much happier with a traditional Thanksgiving. E to the something looks a lot better than this complicated business. So I'm going to say, I will imagine that this is just e to the u. And then I'll define u to be x plus 2, so really I haven't changed anything at all, right? I'm still talking about the same function. I'm just in Canadian dollars instead of American dollars. And this function is easy for me to differentiate. Right? So if I want to take the derivative with respect to x here, g prime of x is what? The derivative of e to the u is e to the u, right? Doesn't change. But this is a u, not an x. So if I differentiate with respect to x, this is a u. I have to use the chain rule here and multiply by the derivative of that expression. Right? Because I'm not measuring the change in u, I'm measuring the change in something else, the change in x. But my function is measured in u's right now because I converted my money all into loonies. And now I just have to plug u back in. So e to the u, that's e to the x plus 2, times u prime. What's u prime? Just 1, yeah. Du dx is 1 here. So that's kind of nice. G prime of x is just e to the x plus 2. It didn't change at all. Yes?
Wouldn't we have known that at the beginning strictly because it's an e base?
So let's see an example where this doesn't happen quite so nicely. Yeah. What if, instead of a nice linear function, a nice monic linear function there, we had something that was different? Even just a little bit different. What if we had e to the x squared instead of e to the x? So now, instead of du dx being 1, you'll notice that du dx is 2x. So something like this might happen, right? The derivative of e to the u is just e to the u times du dx, right? U is really x squared, because I defined it to be that. And because I defined u to be x squared, du dx is 2x. So there's this 2x. And in general, I like to put these kind of polynomial coefficients in front of exponentials, just to kind of avoid any confusion about whether this is up in the exponent or down. So 2x e to the x is the way I might like that written.
Okay, how come e to the x squared is 2x and not e to the 2x?
Oh, this should be e to the x squared, sorry. Yeah, sorry. I'll let that 2 off. This should stay the same. Was that the question?
No, in parentheses the 2x.
Uh-huh.
How come that was not e to the 2x?
This is the derivative of u with respect to x, right? This is just how u is changing. It's not the entire function, right? It's
Oh, it's just the x squared.
it's just that little x squared part.
So if e is the outside and x squared is the inside, you define the derivative of the outside and then the inside.
Yes.
Multiply them together.
Yes.
Because these u's are confusing me.
So this, the reason that I presented it this way, there are a couple of reasons. One, I think that as we kind of like move forward, this type of recognition that I'm taking the derivative with respect to x, and this x doesn't match up with the u that I defined, will be helpful. That will be. And then as you move into Calculus 2, for those of you taking Calculus 2, you're going to start wondering about what happens if you do this differentiation process backwards. Right? Here's the derivative. Find the original function. And there will be situations in which this u type of language will be helpful. There's a process called integration by substitution where that's going to come invaluable. So there is a reason here. But you will find kind of like as you do more and more of these problems, which I really, really recommend, do as many of these problems as you can. Get it into your bones. You're going to just start identifying, oh, here's the inside function, here's the outside function, and I'll follow this pattern. Right? So if I have something like e to the x cubed plus 2x squared plus 4, right? Then I know that the derivative is e to the x cubed plus 2x squared plus 4 times 3x squared plus 4x. Right? This is e to the something. Right? The derivative of e to the something is e to the something. Right? This is e to the x, the derivative is e to the x. The derivative of e to the x cubed plus 2x squared plus 4 is e to the x cubed plus 2x squared plus 4. Okay. But this was a big complicated inside function. So in order to adjust for that complication, I have to multiply by the derivative of that inside function, which in this case is 3x squared plus 4x. I have something that looks like 4x minus 3 raised to the 99th power. Now, if I really wanted to, I could multiply all of this out, and I would get a polynomial with like 100 terms in it, and then I could take the derivative really easily. But it would cost me like, a year of my life, which I don't want to do, right? Instead, I think that there's an inside function here that's complicating this expression. This is really, at its heart, something to the 99th power. And if you have something to the 99th power, then the derivative is 99 something to the 98th. So that something is 4x minus 3. Right? X to the 99th is 99x to the 98th. So 4x minus 3 to the 99th will be 99, 4x minus 3 to the 98th. But this 4x minus 3 isn't just an x. It's a 4x minus 3. So I have to multiply by the derivative of that expression, which is 4. So that's going to be 396 times 4x minus 3 to the 98th. Okay?
So when you find the derivative of the inside, it would just be 4 to the 99.
The derivative of the inside is not 4 to the 99. The derivative of the inside is just 4. Right? The inside is just 4x minus 3. The shadows here are
The outside,
causing.
the first part.
Yeah, so the outside is something to the 99. It's 4x minus 3 to the 99. But if I had something to the 99th, I'm expecting the derivative to be 99 something to the 98th.
Yeah, but when you find the derivative of 4x minus 3, it's just 4.
Yeah, that's here on the outside. I multiply by it after.
Okay.
Right? At first, I'm thinking that this 4x minus 3 is changing. So what's the derivative of this expression as 4x minus 3 changes? It's going to be 99, 4x minus 3 to the 98th. Just like I normally take derivatives. But this 4x minus 3 is going to change at a different rate than just an x would. So I'm going to multiply by the rate that is changing. That's the times 4. So back when we introduced a rule here, here we go. Our rule, right? df du, du dx. Right? I'm treating that u as if it's the x, right? I'm taking the derivative with respect to that thing. Right? It's still here, right? This is f prime of u. It's not f prime of u prime. I haven't changed the inside function. The inside function is still exactly the same in the first factor of this derivative. Where I adjust for the inside function is after. I multiply by the derivative of that function at the end, instead of plugging in a derivative to begin with. Does that make sense?